To this point, we've only shown you one way to design behavioral SystemVerilog, that is, with the continuous assignment statement. Using it, you can easily build Boolean logic and truth tables and multiplexers. However, the continuous assignment statement has some limitations. It cannot be used to model the behavior of sequential logic, that is, logic with memory or that is synchronized with a clock signal. Nor can it be used with more familiar programming constructs such as if statements, loops, and switch statements. There are cases when you want to build behaviors that are more complex and that are comprised of multiple lines of code, especially when writing test benches. That is code that is used to drive the inputs of another design under test and to read its subsequent outputs in order to validate its correctness. Test benches are designed for simulation only. They're not designed to be synthesized into hardware, so you can afford to make test bench code more complex since you don't have to worry about it being converted to hardware. So for this, you can use a process, which in SystemVerilog is built using the always statement. An always statement executes in the same way as a continuous assignment statement, in the sense that its outputs are updated whenever any of its inputs change state. So from the perspective of an outside observer, there's no point in time in which an always statement is only partially executed. But always statements have three features that a continuous assignment statement doesn't. The first is that its outputs can be determined using multiple lines of code whose control flow is sequential, meaning that one line of code builds on the results of previous lines of code. However, this is only an attribute of the program structure of the code itself and is a designer or programmer convenience, because when the always block is synthesized, it's synthesized into a single logic circuit, at which point there's no distinction between different lines of code. The second is that an always statement can conveniently set multiple outputs. Now, a continuous assignment statement can technically set multiple outputs by using a curly brace concatenation operator on the left-hand side of the assign statement, but in general, assign statements are used to assign just one output at a time. An always statement, on the other hand, can set multiple outputs very easily. The third is that an always statement decouples the notion of its input signals with that of its activation signals. In other words, in an assign statement, all the signals listed on the right-hand side are both inputs in that they determine the value of the output, as well as activation signals, meaning that their state change triggers the assign statement to update its output. In an always statement, the inputs are any signals listed on the right-hand side of an assignment or that appear in a conditional expression. The activation list can be the same set of signals, in which case the always block is modeling combinational logic. So it basically then becomes a complex form of a continuous assignment statement. However, the activation signals and the input signals can also be different, meaning that an input signal can change without activating the always block. For example, you might remember from CSCE 211 that a D flip-flop will ignore changes to its D input until there's a change in the clock input. And having a different set of activation signals versus input signals is how SystemVerilog defines sequential logic and memory. Always statements are also used for writing test benches, test code, test harnesses that are not intended to be part of your design, but instead used in conjunction with a simulator in your design to validate the functional correctness of your design. In this case, the always statement is often used in conjunction with delay statements to drive inputs into a design under test and read the corresponding outputs. Delay statements will disqualify a module from being synthesizable, but they, as I mentioned, they often appear in the test bench code. This gives three different styles of always statements. The first is for using an always statement for combinational logic, and so always statements in this style could also be rewritten as a continuous assignment statement. But the choice of using an always instead of an assign statement is a matter of personal coding style. In this mode, in this style, you begin the always statement using the always underscore comb, C-O-M-B, keyword. If the always statement requires more than one statement, you can use a begin and end keyword to form a basic block, much like you'd use curly braces in Java or indents in Python. So recall that a mux can be performed using an assignment statement, a ternary operator. The same behavior can be made with an always statement, but in an always statement, you can take advantage of an if statement. Note that if statements, loops, and switch statements can only be used inside of an always block. In other words, the only code that you can put outside an always block is structural code, where you're instancing other modules, and continuous assignment statements. All other code constructs can only be used inside an always block, or an initial statement, which is similar to an always block, which I'll get to soon. One of the disadvantages of using an always statement from a readability point of view is determining the outputs of the always statement. The outputs are any signal that are assigned inside the block, but they're not explicitly listed. Sometimes they're not obvious, but it's important because every always block is synthesized into a logic element. So this has an important implication when it comes to the possibility of double driving signals. You can't have more than one always block that drives the same signal, since this would put the signal in contention, or it would be double driven. Another complication of using an always block comes from the potential for activating an always block and having it follow a path of if statements, a control path, that doesn't result in setting all of the possible outputs of the always block. For example, if you were to omit the else part in our multiplexer code, then the out signal would not be assigned when the block is activated when the value of select transitions to 1. This behavior will cause the synthesizer to create a latch, which is a memory element that doesn't use an edge-triggered clock signal. This is always an unintended behavior or an unintended side effect of buggy code, and often will generate warnings from the compiler, but sometimes these warnings are easy to miss. You can avoid any possibility, though, of latches or of the synthesizer generating latches from your code by assigning all the outputs to a default value at the beginning of an always block. In this case, the out signal appears to be assigned twice when select equals 1, but the outputs of an always block are determined only by the last assignment that occurs within the block after the block is activated. Since always blocks are atomic and there's never a point where they're only partially executed, you don't have to worry about there being a time in which the state of the out signal changes from its default value to its final value. You only see it change to its final value. Within an always statement, in addition to if statements, you can also use switch statements, or rather in SystemVerilog they're called case statements, but the structure of which you're familiar with from Java and C++. So for case statements, you use the syntax shown. Be sure that you use begin and end statements whenever you're comprising a basic block consisting of more than one line of code. Also, you can use the question mark in the case values to denote a don't care value. Next, I'll discuss the second use of an always statement, which is to build sequential logic. And later in the semester, I will present a thorough lecture on sequential logic. But unfortunately, I need to cover a quick and informal treatment of sequential logic in SystemVerilog in order to allow you to start working on any of the projects, because it's really not possible to design anything non-trivial in HDL without sequential logic. And project 1 will require a small amount of sequential logic. Building sequential logic doesn't require a lot of code. Basically, you use the always_ff variant of the always statement. So it's the always_ff keyword followed by the @ symbol, and then a list of activation signals in parentheses. Typically, the activation signals are pause edge followed by the clock signal, meaning that the block would trigger on the rising edge of the clock. And you can optionally follow that by a comma and additional signals. For example, you can say pause edge reset if you want your always statement to activate on the change of reset, meaning that you can support asynchronous resets. In other words, you can reset the state of your sequential logic without having to wait for the clock. In this example, the always block is activated on any change of the reset signal or the rising edge of the clock signal. In other words, if the reset signal becomes 1, then the value of Q, the output value, or I should say the state of Q, will clear to 0. If the clock transitions from 0 to 1, rising edge or positive edge of the clock, and the reset is 0, then the value of the D input is transferred into the Q output. In any other case, the D input is ignored. You can extend your flip-flop to hold multiple bits by changing the width of D and Q. When you have a flip-flop that contains multiple bits, it is sometimes referred to as a register instead of a flip-flop. You can also incorporate different behavior into an always block. In other words, it doesn't have to just be a straight-up flip-flop. For example, instead of saving the value of D, you could increment the saved value on Q. You can combine the ability to initialize the value of Q using the D input with the ability to increment by adding some additional control signals. Notice that the always block uses the less than equal as opposed to the traditional equal sign. Okay, so you can use the equal sign or the less than equal sign whenever you assign an output in an always statement. The less than equal sign is called a non-blocking assignment. By convention, you should use the non-blocking assignment whenever you write sequential logic. And you should use the normal equal sign, which is the blocking assignment, when writing combinational logic. The actual difference between blocking and non-blocking assignments is a bit difficult to describe. But I will try. Any signal assigned with a blocking assignment inside an always block will propagate down to the right-hand side of any expression that references that signal made after the assignment, or any conditions in which that signal appears after the assignment. Non-blocking assignments are not visible to the process until the next activation. So in other words, a blocking assignment is the assignment takes effect right away, whereas a non-blocking assignment doesn't take effect until the next time the always block is activated. This can sometimes get a little bit more complex than this description implies. I've found that this behavior applies actually to not just within one always block, but applies to all activations that correspond to a particular event, as opposed to being local within a specific always block. This has caused some unexpected bugs in some of my SystemVerilog designs, so it's best to stick with the convention, meaning use the blocking or single equal sign when building a combinational logic, use the less than equal or the non-blocking assignment when designing sequential logic. Okay, so now let's discuss the third use of always blocks. Test benches. Let's begin with a simple module that we want to test, shown here. Now let's create a test bench module that instances our module that we want to test. We need something inside our test bench that drives the inputs to the design we're testing, or the design under test, as well as something that checks the output. A raw always statement can be used without a sensitivity list, which causes it to trigger continuously. This is not synthesizable, so it only works in simulation. Also, inside an always block, you can use a delay statement, which is also non-synthesizable. Its syntax is a hash mark followed by the delay in simulation time units followed by a semicolon. Now note that a simulation time unit is normally set using a compiler directive at the beginning of your module file, using the syntax shown, basically accent grav timescale followed by the time unit for the simulator and a slash, and the time precision and no semicolon. So in other words, the backwards apostrophe accent grav is equivalent to the pound or hash sign when defining compiler directives in C and C++. But if you don't use this directive in your module, then the simulator will use whatever default time unit it uses, and this will vary by simulator, and usually this is fine for us in this class. But the assign statement without a sensitivity list combined with the delay statement provides a convenient way to generate a clock signal. So you can say, for instance, always begin, set the clock to 0, delay for 5 simulator time units, set the clock to 1, and then delay for 5 simulator time units, and repeat. Also, there's a variation on the always block called the initial block. The initial block is used to set one-time initial conditions. In the case of synthesizable SystemVerilog, the initial block is used to initialize memory elements. But in a test bench, the initial block is used as the starting point for the testing procedure. So for instance, I can set a reset signal up by beginning an initial block, setting my reset to 1, waiting 5 simulator time units, and then setting the reset signal to 0. That will give me a reset pulse at the beginning of the testing. Likewise, you can use the initial block, either the same one you used for reset, or you can create a new one and use it to drive the input for your design under test. So in this example, I am setting the input values A, B, and then waiting for 10 simulator time units in between each set of inputs. You can also use an initial block, again, either the same one that you use to set the inputs or a separate one, to check, to verify if the actual output coming from the design under test matches what we expect the outputs to be for a correct design. So in this example, I added a line of code after each delay where I check if the actual output, which is Y, matches the expected output, which in this case I just hard code as a numeric constant. If they don't match, then I use the display function to print an error message. Now, a few things here. Notice that the if statements come after the setting of the corresponding inputs and the delay. This is important because the output of combinational logic elements requires a non-zero amount of time for the result to propagate. So, in other words, you have to put a delay after you set the inputs in order to see the corresponding output. Also notice the display function, $display function, which is a Verilog task that accepts formatted strings much like printf does in C and C++, if you're familiar with that. Instead of having to hard code the inputs and the matching corresponding outputs in the SystemVerilog file, it may be easier to specify a separate file or a test vectors file that contains this information. This way we can keep the test inputs and outputs separate from the test bench implementation itself. To do this, you need only to declare a special 2D array to hold the test vectors and initialize it in an initial block. So we declare our test vectors, and the syntax is a little different than other languages, but the first range of indices 2 down to 0 represent the width, and the second indice range 9 down to 0 represents the depth or the number of test vectors. So we have the width, which is 3 bits for A, B, and Y, the 2 inputs and the expected output that corresponds to that, as well as the maximum number of vectors that can be stored, which is the depth, which in this case is 10. This is different from C and Java, where when you have a 2D array, the depth comes first and the width comes second. This is the opposite. In this case, the width comes first and the depth comes second. We can add an initial block that calls another SystemVerilog task, or actually just Verilog task, readmemb, that reads the data from a vectors.txt file into the test vectors array. And I'll get back to the formatting of that file in a minute, but first, what do we need to write in the test vector implementation to use the test vectors? Well, we can use a for loop inside an initial block. We declare the integer I outside the initial block. Inside the integer block, we set up a for loop for I equals 0, I less than 10, I equals I plus 1. There are 10 test vectors here. Notice there are I equals I plus 1 and not I plus plus, because, as I mentioned, Verilog does not support self-assignment operators, so I plus plus will not work. The for loop basic block also is denoted with a begin and end keyword, because there are multiple lines of code inside the for loop. The first thing we do in there is assign the A and B, which are the inputs, to test vectors number I and bits 1 down to 0. Now notice here again, the syntax is a little odd because when we declared test vectors, the first index that we specified was the width and the second was the depth. But now that when we use test vectors, the first index is essentially the depth, or which test vector, and the second index is the columns, or having to do with the width. So again, that's a little strange. The next line of code says if A equals 1 apostrophe BX, then $finish. This is a trick where once we read the first test vector that wasn't initialized, it'll return an X. But notice there's 3 equal signs in this if statement. The 3 equal signs allows you to perform comparisons where one of the sides or both of the sides of the comparison is a non-binary value, in other words, an X or a Z. If you just use 2 equal signs here, then that if statement will always, the condition will always evaluate to false, even if A in fact was an X. The difference here is that a 2 equal signs represents a synthesizable comparison. The 3 equal signs is a non-synthesizable comparison, and the idea is that in synthesized code you wouldn't be able to compare to an X or Z because X and Z doesn't exist in real hardware. Those are only concepts used in the simulator. So the rule of thumb here is that when writing a test bench, use the triple equals, or conversely the explanation point double equals for equal and non-equal respectively, and in synthesizable code you would use just 2 equals and explanation point equals. The $finish function is a way to stop the simulation. Okay, now that we've built a test bench, I will show you how to actually simulate it. I'm going to begin by launching the virtual machine for the class, which we'll show you how to set up in a separate video. Once it's started, you can open up a terminal using Control-Alt-T, and I find that the default font size is a little small for my taste, so we'll go into Terminal Preferences under the Appearance tab, and then you can adjust the font size. I boosted mine up to 20. That's a lot easier to read. Okay, so I'm going to start out by creating a directory for my design and going into that directory. And now we will enter the SystemVerilog for the design that we'll be testing, which I called my module, so we'll call it mymodule.sv. So now we've got so I'm using Vim as my text editor, but you could use whatever text editor you feel most comfortable with. So I'll go ahead and type out the module. This is the same module that I used in the lecture. This module is called my module. It has input clock, reset, X and Y, and output Z, all of type logic. Make sure you don't forget the semicolon on the module line. Now, the behavior of this module is sequential. It's clocked. So we'll have an always FF block, which is sensitive on the positive edge of clock and reset. So if we have a rising edge of reset, we'll activate the always block. If the reset is high on that activation, then we will reset Z to 0. Otherwise, Z will take the Boolean expression of not X and not Y, or X and not Y. So simple Boolean expression. Now notice I don't have a begin and end on either the always statement or the if statement, because in each case there's only one line of code involved. If you have more than one line of code, then you need a begin and end. And so this would go for the if statement and the always statement. Now notice the test bench has no inputs or outputs, and that is normal for a test bench since all of the signals are generated internally in the test bench, and all of the outputs are also validated within the test bench. So generally speaking, you won't have any inputs or outputs in your test bench. Now the test bench, I am going to declare internal signals for all of the inputs and outputs to my design under test, DUT. So now I will instantiate a design under test, which is of course my module, and I will connect internal signals to its pins. Clock and reset have the same name externally as they do internally within my module. The X and Y inputs on the module are connected to the signals A and B inside the test bench, and the Z output is connected to the signal Y inside the test bench. This is confusing, possibly needlessly so, but I'm doing it here to illustrate how signals can be renamed across the design hierarchy. The next thing I want to do is I want to set up the clock signal. I'll do that with an always block that will just toggle the clock from 0 to 1 and back again. Now the clock is 0 for 5 units and 1 for 5 units, so the clock period is 10 simulator units. So if I want to wait for a clock signal elsewhere in the design, I would wait for multiple, wait for 10, or multiples of 10 for multiple clock cycles. So one of the things I want to add to the initial block that sets up the reset signal is a special task called $WLF dump vars, which will tell the simulator to record the state of all signals in the design, regardless of whether they're in our waveform window or not. This is a convenience for us because this way we can add signals to the waveform window without having to rerun the simulation to get the data. So now I will set reset to 1, wait 7 time units, and then set reset to 0. The 7 is just kind of a random number that I put in for the reset period. I usually use a value that's not a multiple of the clock or even a multiple of half clock. The next step is to set up the test vectors. So I will declare the test vectors using the width listed first and the depth listed second. The depth is just the maximum number of test vectors, and generally speaking you'll have less than that. Then I'll have another initial block that will initialize the vectors from a file vectors.txt. Now I'm going to add the initial block that will drive the test vectors into the design under test and check the results. For this I'm going to use a for loop, so I'll declare an integer I, and before I do anything, I'm going to want to make sure I wait until after the reset period before I start sending my test vectors in. So I'll wait 10 time units for this, then I'll have my for loop that will walk through each of the test vectors. Inside the for loop I will assign A and B to the most significant 2 bits of test vector I. This way when I specify my test vectors from reading from left to right, I'll have the 2 inputs and then the output. After this I need to check to see if I'm done with my test vector, so I'll check to see if I've read past the last vector stored in the array. If I had, then I'll get an X value out. Note that SystemVerilog uses X for quite a few things. X is a conflict, it is a don't care, it's also used as an undefined value, which is what we're using it for here. So if you have an uninitialized memory, then it's undefined, so you get an X value. Now if I didn't, if I do get an undefined value, then I'll finish the simulation, but if I didn't, I am now going to wait 10 time units. Now this This is what you would have to have a wait in here even if I was testing a combinational design under test. But since this is a sequential design under test, it's even more important that I wait for exactly one cycle, because the output will be updated after one cycle. Now, inside the test vector, I am using the least significant bit of the test vector as the expected output. This is, of course, arbitrary. It depends on how, what order you want to type in the test vectors, but generally the expected outputs are on the right-hand side of the test vector, which is the least significant bits. Now, if the actual output y doesn't equal the expected output, then I will display an error message. This is a formatted error message where I will include the vector number in the message as well as the time in the simulation time where it happened. Now, this is important because if you don't have the time in the error message and you get an error, you're not going to know where the error occurred in your waveform. I'm also going to list what the expected value is in binary as well as the actual value. The actual value, of course, is shown in the waveform, but the expected value is only in the test vector. So printing the expected value is important. The display task works exactly like printf in C and C++. So now I'll save the test bench, and now I'm going to open the test vectors file. Now, if you remember, I called it vectors.txt in the test bench. The test vector files can have comments, and so it's useful to have a comment that defines what the format of the test vector is. In this case, there's 3 bits. The inputs are A and B are in the 2 most significant bits, and Y is the least significant bit. Since I have 2 inputs, I can put all 4 input combinations. And the expected Y value comes from the logic, the Boolean logic that is in the design under test, which I just worked out on paper. Okay, so now that I've got my SystemVerilog files written, before I can simulate them, I need to compile them. The compile command is vlog. Now, of course, it depends on which simulator you're using, but since we're using Modelsim now, I'm going to use the vlog command. So when I compile each of these, it will store the compiled form of these modules in the current directory. So I have to compile my module in testbench. If I make any changes to these, I need to recompile them before I rerun them. Now, you can also compile these from within the simulator itself. I'm doing it at the command line now just because I haven't gone into the simulator yet. Now, I can start the simulator by typing vsim and testbench. Now, you wouldn't specify the extension there because it's just the testbench as a module. You're saying vsim and then a module name. The module that you provide here is the top level module. So I'm going to simulate as testbench as the top level, which is the root of the design hierarchy. And of course, that will include a simulation for my module because it is instantiated within the testbench. When you start the simulator, you'll see this window. Currently, it is configured with 5 different panes. The leftmost is the structure. It's literally just the design hierarchy. So you can see testbench at the top, and then you can see the DUT, the dot, and that is represented as a tree. Then we have in the middle, on the top middle, we've got the objects, which are all of the signals and memories contained within whichever of the modules in the design hierarchy is highlighted. So in this case, it's testbench. So we have A, B, and Y as opposed to X, Y, and Z, which is what we'd see if we were inside, if we clicked on dot. Then we have processes. The processes are the always statements. So you can see we've got 4 of those. And then on the right is our waveform window, which is currently empty because we haven't dragged any objects into it to plot. And then the bottom is the command line interface, which accepts tickle commands. So anything you do in the GUI, any button you press in the GUI will show the corresponding command in the command line window, and then if you want to automate things, you can collect those commands and put them into a file, and then you can run it like a script using the do command, or you can, if you just go to the file drop-down menu, you can run a script through there as well. So the first thing I'm doing here is I'm going to select all of the signals that are signals and memories that are in my test bench. Now I say memories because the test vectors are technically a memory because it's a two-dimensional array, although there's not much of a distinction there, except that I mentioned that the memories won't get recorded unless they're plotted, and I think Modelsim does that just to save disk space. So I'll drag those over to my wave window, and then you can move the little divisions around. And so to run it, there's literally a button at the top right next to where it says 100 picoseconds. You can hit that button and it will run for 100 picoseconds. Now, it's not shown here, although you can see it in the settings, but I mentioned earlier that if you don't specify a timescale in the SystemVerilog file, the simulator will use a default timescale. In Modelsim, that timescale is picoseconds. So one time unit is 1 picosecond. So when I hit the run button, and that's the little down arrow button that's to the right of the run interval, which is 100 picoseconds, it's going to run for 100 simulator time units. But the problem here is that my simulation, because there's 4 test vectors and they run for 1 cycle at a time, and of course there's that that delay at the beginning where I do a reset. It's basically the whole test bench only requires 50 time units to run through my test bench. So as soon as I hit the run button, right away it says, are you sure you want to finish? Now, if I hit yes on that, it will stop the simulation. I think it actually closes Modelsim. I'm going to hit no on that so I can leave it open and explore and check things out a little bit. Now, if there were any error messages printed from the $display task, they would be printed there in the command line window at the bottom. One thing though that you will notice, we don't see any of those, but we do see a warning that says too many digits 3 in data on line 2 of file vectors.txt. So the max is 1. Now, why are we getting that error? Well, it turns out that was a bug in my code. I had 3 digits because there were 3 bits. But in the test bench, I read the test vectors with the read mem h task. And so it is interpreting each of the 3 digits as a hexadecimal digit and not as a binary digit, which is why I'm getting this error. So I need to go back to my test bench and I need to fix that bug by changing read mem h to read mem b. Yeah, see, that's the problem. So I go back to my command line now. Because I launched vsim without an ampersand, it was in the foreground. So I'm going to hit Control-Z, suspend it, and then type BG to push it into the background. That way I can use this terminal to make my correction. Now I'm opening up testbench.sv. I'm going to fix my bug. So this is readmem B now. And reload in the editor window. And then there's a shortcut here. Instead of recompiling with vlog back in the terminal window, which I could have done, I want to show you an alternative way. You can go to the library tab over in the leftmost pane and hit the expand the work. Now let me quickly explain this. Notice we have some libraries here listed. We have several libraries. These are simulation libraries that are included in Modelsim. The one labeled work at the top is where all of your designs will go, all of your modules. So if I expand work, you'll see all the modules that you've compiled in the current directory. If you right-click on testbench, we can say recompile. That will recompile it, and then I have to reset the simulation by hitting the little button to the left of the little time period field there, and a little up arrow. Looks like a little up arrow. That'll reset everything, and when you reset the simulation, it also reloads your compiled modules. And now I run again and notice that warning message didn't come back. And also I didn't get any errors from the test bench. So that would imply that everything worked, but in order to just kind of sanity check that, I'm going to go over to the Wave tab over here, and I am going to, I can't find the zoom button. I don't know why that doesn't show up by default. So in order to zoom in, I'm going to use the middle mouse button and just draw my zoom there. And so you can see there are clearly 4 test vectors there. There's now one of the things you'll notice here is that the inputs get asserted on the falling edge of the clock, and the reason for that is because the clock in the test bench starts out as 0, right? So that means that the first edge of the clock is a falling edge, and then the clock period is 10 units. So every 10 units of time will have a falling edge. So because the test vectors wait for 1 cycle before they start asserting, the test vectors end up changing on the falling edge of the clock, but then you'll see that Y, the output of the design under test, is changing on the rising edge of the clock. So we're changing the inputs on the falling edge of the clock, and we're seeing the outputs change on the rising edge of the clock. So the design under test only has a half cycle to actually perform its logic, and that's okay. But again, I didn't explicitly put in there that the inputs should change on the falling edge of the clock. It's just worked out that way because of the way I set up the clock signal, in that the clock goes from low to high at the very beginning of the simulation. Now, if I could go back in my test bench and change that and invert that, in which case the inputs would change on the rising edge, and then the resultant outputs, the corresponding outputs, would change on the rising edge as well. So in order to check to see if the test bench error checking is working at all, I'm going to introduce an intentional bug where, instead of checking if the actual output from the design under test matches the expected output, I'm going to print an error if they do match, which is obviously not the behavior that you want, but this way I should see an error message printed out for all 4 test vectors. So this will allow me to check the formatting of my error message. So I'll recompile, reset, and run it, and you can see that all 4 of my vectors report a failure, and you can see how the error messages would look if they were printed. Okay, well, that's all for the tutorial, and in the next lecture we'll show you how to get the virtual machine set up on your personal computer so you can try this out.